Doug Connelly is Principal Geochemist at the National Oceanography Centre in Southampton. Doug studies essentially the chemistry of hydrothermal vents, and indeed we've done several cruises together in the Antarctic searching for vents down there. Doug is going to talk to us about finding life once we found a suitable planet.
Thank you very much. Thank you, Alex. Thank you, William, for organising this and getting me to come here. It's a little bit of a departure from what I normally talk about. I did go about a decade ago to JPL and do a talk on how we might do some of the sensors we were developing and use those for searching on other planets. And that's what I'll round off at the end as sort of where the future is. Alex did cover quite a bit of what I'm going to talk about, but anyway, no matter. I've got some new videos and a new site. So we've got this issue of the fact that we're going to go to one of these planets or moons. Basically, Europa is going to be, estimates are 100 kilometres thick of water. We've only been down to about 5 kilometres to find vent sites. We generally say that 6 kilometres is our sort of limit of where we generally look in the oceans. That's sort of operationally defined because basically most of our instruments are actually only capable to go down 6,000 metres at the moment. We are stretching those limits, and there are manned submersibles now going down to the bottom of the deep troughs on the planet. We've sort of constrained ourselves mainly to looking around for basically hydrothermal vents, and the discussion came up at the coffee break as to do we know they're there to begin with? Well, basically with the advent of plate tectonics, these are the places we look. Is there a pointer on here? I guess there is somewhere. Right. So we generally have spent, the first vent sites were found here in the Galapagos area. We've gone down the ridges and, we've found, this is the stuff that Alex and I found. Alex also found one down here. We've got the new Cayman vents up here. We generally tend to stay on the spreading centres, and as an interesting analogy with this sort of the work we did down in Antarctica here, we went over a vent site, a rather distal vent site, diffuse spreading vent site, which was taken a photograph in 1963 by the British Antarctic Survey, and they just didn't recognise what it was. So basically we went back there, and it's the same geological feature, it's perfect, and we went back there for 5 years running, and so the same feature doesn't change with hydrothermal vent organisms. So basically we'd have tipped the world on its head, and we could have started actually looking for vent sites in the high latitudes rather than the nice warm parts of the planet, which are relatively easy to get to. So we've concentrated here. So we've gone along these, but again, it's how do you find them? And coming back to what Alex talked about earlier on, they do give us some clues. We've got this recharge center, we've got these fluids coming up, as Alex pointed out from that big chart of different chemistries. They throw a lot more compounds into the water than are normally there, so we can use that to look for things. And basically we can, in the good old days, we would use these CTD systems, and we'd be going down the water column. We'd have apply, at this point, a very basic set of rudimentary sensors. We would either look for temperature, which you've got to get very close to a vent site to find temperature, because the deep ocean tends to neutralise out the temperature from a vent site, even a 300, 400 degrees vent site. So you'd look for basically smoke in the water, so the classic black smoke was coming out, and we would spend some time basically dropping down a CTD, and we'd make the ship move forward at 0.4 knots, and we'd drag the CTD up and down the water column until we found some nice sort of dirty water. And there's a bit of misnomer this because it should actually taper out. And we'd go through, and we'd keep going through until we went out the end of it. So we'd assume we'd sort of constrained partly our vent site. Now, there are different types of spreading centres on the planet. Some types, the mid-Atlantic ridge particularly, is typified by an axial trough. So if your vent site's at the bottom of it, it's great. You just run your CTD along the trough, and you contain all those nice chemicals in the bottom, and you can measure them. Unfortunately, as Alex alluded to, when we went to Antarctica, the spreading centres in Antarctica aren't nice troughs, they're actually ridges. And the vents, this gives you, each one of these blue spots is a CTD sample, which basically we did 594 CTDs over the period of, I think, 3 weeks before we actually started to constrain it in. Every yellow star is where we found an indicator of a vent site. So some dirty water, smoky water in the water column. So as you can see where we got excited, we did a lot more CTDs around here, we did CTDs here. Coming back to sort of why we first used to look, we'd go and actually look at the geology and morphology, and we think, oh look, that looks like something interesting. So I always refer to my geologist friends, I'm a chemist, we've never yet found a vent site looking at geology. We've never gone, oh, that's got to be hydrothermal vent in that trough. because it isn't. They're actually not in place. You think they are in the broadest sense. They are along the spreading centres, but actually, so when it comes down to it, they're I've got the same figure again. And again, Cayman Trough. This is the latest work we did. So the spreading centre here, Cayman Trough's only 100 kilometres. I think it would be easy to do. Look at the different places. So we've got a complication. This is a so-called ocean core complex, which is a rather unusual geological feature. It's actually where a piece of the mantle is being exhumed onto the seabed. So Lost City, I'll come back onto that. Lost City sort of does that. So you end up doing tons of CTDs. If I can escape out of this, I can show some videos. I was hoping to put it on second screen, but oh gosh, where am I? There we go. So here's our little CTDs. If it plays, probably won't. Oh no, media player. Sorry, I work on a Mac, not a PC, and it's never the twain shall meet, it seems. So again, CTDs, again, very laborious. This is actually some work we've just done in the Pacific, going down to 4,000 metres. That little bit there is about 15 minutes just to get the system in the water. So you're talking sort of 10, 11 hours for each sample. And then basically where we've moved on to is starting to use some, let me get back to Photoshop. Where are we? Oxford. Oh Lord, it's not the best, smoothest one. Sorry about this. Just big files. So what we've moved on to now is actually to using some of the new technologies, sort of remote access. Now this is Otto Sub. This is developed in the UK. And it's just had a big £10 million investment from the UK government as one of the great ideas for the future. And basically, using Otto Sub, you can put sensors on there. The nice thing about it is you can throw it over the water. You can go leave it into the water column. It will go down. It will do a sort of a survey on the bottom to give you an indicator of what it does. So this is a survey we did. This is basically 50-metre spacing lines. So we just left it to mow the lawn going along across the bottom. The sensor we had on this is a new sensor developed by Japanese colleagues of ours, Koichi Nakamura, which measures redox potential. So whereas before we had smoke, and that's great, you can see smoke in the water column. The problem is the particles from hydrothermal vents go a long, long way. And so you can really only constrain sort of almost to ridge crest access as to where those vent sites are. You're referring back to that original site where we had hundreds and hundreds of CTDs. All of those yellow stars gave us a positive signal. Using this, we did the same thing in the Cayman Trough. We used the CTDs to constrain a sort of 50 by 50 kilometre 5 kilometre by 5 kilometre box where we thought the hydrothermal vent site might be in. Basically, because we'd run the CTD and if you get signal, then it would run out. Put this down. This was basically did a 24-hour survey, and these EH signals here, so even though there'd be lots of smoke all the way around here, this is all in a smoky area, these EH signals give you an indication where you've got lots of hydrogen sulfide coming into the water column. The half-life of hydrogen sulfide is very short, it gets oxidized, so it gets diluted away. So where you find smoke and hydrogen sulfide generally tells you you're within, sort of in this case, we're within about 500 metres of the vent site. So we then deployed something to go and look at the seabed, and in this case we were hoping to use ISIS, but since we'd broken it a couple of years before in the Antarctic, which we won't talk about, we were stuck with basically a towed camera system, and we did manage to find the hydrothermal vent site. So we'd cut our survey time down from finding a vent site from sort of 3 weeks down to less than a week. And so it was really, really good. Interestingly enough, in the Cayman work, coming back to some comments earlier on, the Mount Dent site here, we've also got a hydrothermal vent site on the top of there. So it's a little bit, where it's analogous to Lost City. It's entirely different chemistry. It's phenomenally rich in hydrogen sulfide. It has no smoke. So the spreading centre, the main hot vent site is here, BB. The Von Dam vent site here is 2.5 kilometres higher in the water column and 15 kilometres away. So we're trying to work out where the energy is coming from that. In Lost City, the argument is it's still mining energy from the spreading centre. We think it may still be mining energy from the spreading centre, so we've been looking at the chemistries of the two vent sites, one here and one there, trying to work out what's happening. Interesting enough, there's tons and tons of metals in the Von Dam site, the BB site, the very deep site. It's extremely hot. It's the hottest vent site and the deepest vent site on the planet, and it will still be the deepest vent site because it's the only spreading centre in that deep water, in those deep waters. It has really, it's more traditional. It's got iron, manganese, etc. Something gets through here. If it is the same solution, same chemistry, all of the metals have gone and lots of hydrogen sulfide has been added. We thought at first, it's a typical lost city, because this is a basic piece of mantle. We think there's serpentinization going along. There'll be plenty of methane, lots of chemistry. It's not like that at all. The mounds there, the chimneys, are actually made of talc. It's the first vent site we found that they are almost 98% talc chimneys, which shouldn't exist on the seabed. It's very unusual. Lost city is calcium carbonate chimneys, and obviously we usually use the black smoker chimneys, which is sulfide. So it's interesting. And another sort of comment back to one of the other comments is the dissolved gases coming from the deep vent site are 50% hydrogen. I got that data on Thursday, which is astounding. I mean, no one's ever reported hydrogen concentrations on that level. Now, there was a paper by Gillian Peterson a few years ago showing that the bacteria living in symbiosis with some of these rumicaria shrimp, which are some of the nice pictures of the typical black smoke pictures, can use hydrogen as an energy source. There's not so much hydrogen there, there's plenty of hydrogen sulfide. There's also been some debate as to whether these bacteria associated with these shrimps can live on iron, use reduced iron, and actually take the oxidation of iron and take the energy as the oxidized iron. It's a great place to look because you've got beautiful white shrimps at the top because they have no iron in these vent fluids, and bright red shrimps at the bottom because they're coated in iron. So that's another the place to look at is they're almost certainly not using the iron. They're probably using the hydrogen. It's an incredible discovery to find that much hydrogen. We're going to work on that. Where we've moved forward now into the future, of course, is the ISIS using the remote operated vehicle. Once you've found your vent sites, obviously the biologists generally push the chemists out the way. Once we've done our job, found the vent sites, get out the way. We're going to do some work on it now. You can do very high resolution mapping. Ignore some of the names of these chimneys because we do need to change some of these names. We're going to get sued if we call them. What do we call it? Actually, we've taken one off. We did have Disney's Toxic Castle, but we thought that was definitely a lawsuit coming. So we're working all this up still. It's an endless process, but you get very high resolution down to sort of 10 metre, 5 metre resolution of the chimneys. So that makes your job a lot easier when you're trying to find things. Looking towards the future, my sort of main role nowadays is actually the development of sensors, in situ sensors. I lead 2 large programs funded by the European Union to look at developing sensors to look at environmental problems. Now, one of those is trying to find hydrothermal vents. That's just my side interest. The real push and the real way we got funded, of course, is we're developing carbonate sensors and pH sensors for the climate system. So being able to deploy them on observatories to look at our changing climate. If we go to these, let's say I went to the JPL meeting, if we go to these sort of exoplanets and other places, presumably we're going to drill through the ice, put an ROV down, or a remote, some type of, not an ROV, an AUV, and go down there. We are going to need things that we can still measure and actually will definitively give us indicators of life. Now, as I say, at the moment, we don't really have many of those. We can look for methane for about 4 hours before the sensor breaks down. It's also extremely sensitive. It's too sensitive. We are moving on so we've got a program called Sense Ocean funded, which was 6 million we got from the EU. And we're looking at developing sensors using a variety of technologies. So we're basically bomb-proofing a series of, it's like a beauty contest. So we're looking at, this is a lab-on-chip system. We're looking at optodes. We're looking at electrochemistry systems. We're looking at anything we can do to measure anything. And I say the big push for this at the moment is the climate science, but associated with that, we do have systems looking at iron and manganese. The reason we want to look at iron, of course, is because of the natural fertilization. And coming in from the Joe Reesing paper from the Nature published on Thursday, we had some work out last year by Jeff Hawkes, who Alex and also knows, showing that the iron from hydrothermal vent sites, particularly in these shallower vent sites in the back hot basins, can get it taken up into the surface ocean. And so what we're trying to do now is, going back to the isotopes comment earlier on, was can we use basically isotopes for iron to see if there's an indicator of a signal from a hydrothermal vent, a pure hydrothermal signal in the upper water column. It's very challenging. Measuring iron isotopes is very challenging. Our next step is to try and do in situ isotope analysis, both for carbon and for iron. And we are using a cavity ring down system, which is going to be difficult to actually put into a system. Our big push in Sense Ocean is to make these cheap and light and low energy, because we're trying to develop the market. It's a commercial development program. So we want to get things that are basically on the size of this. not on the size of the in situ mass spec that Rich Cimilli has from Woods Hole, which is great, which is the size of this desk, which is only really used for sort of ROVs or for coastal work. There is some, we do have great opportunities coming forward, and the good thing is both the UK government and the EU are putting a lot of money into this sensor development. The challenges of taking it into space, we're actually talking to the sort of exploration guys, it was actually quite interesting, are very similar. Again, it's space. Space is always going to be a problem when you're sending anything onto a rocket into space. Weight, energy usage, chemicals, actually waste, coming back to the idea we don't want to contaminate any place we go with actually our own stuff. And that not just biological contamination, that's actually chemical contamination as well. A lot of these wet chemistry techniques, we use very toxic chemicals. At the moment in the ocean, the way we do it is we collect them. We have a waste bag and we collect those, and we're able to do that. And that's relatively simple. Going into space, that may be more of a challenge. It's, again, longevity. It's fine, we've got sensors that can do really brilliant, precise measurements, but they only last for about a week. Our big step at the moment from the ocean is trying to get something that we can put on the Argo buoys around the Pacific and the Atlantic and try and leave them there for months and months and months. We are moving on to that. We will get there eventually, as I say. These are the vent sites from Cayman. They're a little bit different to the ones down in Scotia, mainly because this is in the South collecting samples. Just a short video to give you an example. In Cayman, they're relatively easy to find because the currents are very, very low because they're in that axial chain, that axial valley. They go up a long way into the water column, and then just a slow one. This is what the AUV looks like when it's actually going into the water. It'll take some time while I'm talking. We don't have any idea of the underlying geological structure of these other planets or the places we're going to go to. So where do we look? I mean, I had some discussion with the JPL guys. They're developing Gattaca on a chip, was what they were calling it at the time, was to find DNA, trying to do some on-chip DNA analysis. We have that already now. We've had a big push through in the last 2 years where we can do DNA analysis on a chip, something the size of this in a package. You do need, the other issue of this is you're going to need some type of intelligent system when you get there. Now, do you rely on the fact that you're going to you're going to actually transmit information back and forward to your on-planet system so you can control it once it's below the ice? Or do you have it actually with some type of artificial intelligence on board? The Americans are working with a system called Sentry, and Sentry it's quite a neat system. It's a hybrid AUV ROV. It can operate in both modes. When it goes in AUV mode, they're trying to develop algorithms so when it finds a sense, when it picks something up that it's looking for, in this case smoke, it changes its direction. So it'll be mowing the lawn just like we do our AUV rather. If it finds something, it will stop and it'll circle around then and do a pattern every concentric rings. As soon as it starts to get weaker, it'll home back in. And they've got this. We've been talking to some guys up in Birmingham working on artificial intelligence for autonomous vehicles, and they do this ant system where basically the system moves and ants find where they are by moving off until they lose a signal and come back. So they're looking at insects to try and find out how to do this. That's probably going to be the way we're going to have to go, is actually trying to make them autonomous and intelligent. And that's actually a huge step. This is our relatively dumb system. It's great. This is the 6,000 meter version. One of the things we've been talking about, and Alex and I have talked about in the past, there's a 6,000 kilometer version of this being tested at the moment. And so one thing we've thought about is basically sending it down the whole mid-Atlantic ridge and trying to find where hydrothermal vents are on the mid-Atlantic ridge. Again, it's sensors and tools. We are moving along all the time. We often hijack systems. I mean, there's no, for versus hydrothermal research, there's not much commercial interest in hydrothermalism beyond some interest from looking at chemicals and drugs from vent sites. There is that interest. So you have to hijack other systems. So the funding I've got going in at the moment, I've just put a big funding in to work on carbon capture and storage, basically with Shell. And one of the things they're interested in is using AUV technology to do large aerial surveys, thousands of kilometres, to actually look where they've got CO2 leaking from a vent site, from there basically a leakage storage site. So we can leverage, and not just technology but money, more importantly, from these systems and try and actually get some of that, use their technology. Oil and gas industry are very interested in doing things well but cheaply, particularly with the oil price plummeting. So we've had some great success with trying to get that. We put a big project in there, and what we're doing is we're using the long-range Otto Sub, and the idea would be Shell are going to operate a carbon capture and storage site in the North Sea, basically off a site called Goldeneye, which is great. But they're going to use this AUV technology and just launch it from the dock and make it semi-intelligent. So it will steam out, it will do this, and it will surface every couple of days, take a signal, get some more information, perhaps a signal back, and tell you what to do. So we can sort of take some of this technology, and all of that presumably will be able to take into space at some point, although I think the AUV here might be a bit too big since it's about the size of this bench. And I'd better finish there since I'm coming to the end of it. This will slowly go into the water. It seems to be a bit faster, but it is a bit like watching paint dry, watching the AUV being launched. Any questions? Sorry. Thank you. Yes.
What is your power source for the 6,000 kilometer version?
It is lithium batteries, rechargeables. At the moment, this system here just uses basically D cells. And the reason it does that is because this one tends to go a bit more around the world, and the shipping requirements for lithium batteries are phenomenally stringent at the moment. We do have a research project as part of Sensocean looking at different energy technologies. And one of the ones they've spent a lot of time with the AUV technologies, because it's relatively big, is actually energy harvesting from the ocean. And again, so that's probably one of the ways to go. I did look, there's a huge US system that's run by diesel. They've got a diesel-operated AUV. It's massive. It's absolutely enormous. It's got a massive diesel engine with it. So it's always going to be a problem. Energy is always going to be a problem. Hence the move towards really low energy systems. I mean, the lab-on-chip system, they measure 5 microliters of solution, and so pumps and things needed for it are actually very small energy. We're working on less than half a watt for each sensor system.
So if you have a gas station every 3,000 kilometers, you could load the battery up and then have it more autonomous.
Well, one of the systems that's analogous to sort of what we might operate on sort of an unmanned station on Mars is what they're doing with the Neptune program off the west coast of America. America and Canada have got a program called Neptune, where they've laid a series of cabled observatories with nodes and docking nodes. And the idea is the next generation for Otto Sub will be able to dock. And we have a big project with a Brazilian oil company based on that. So they'll do their survey, they'll go back in and recharge, upload their data and just dock. They won't even come to the surface at all. And that's a nice sort of approach to take. The other one, of course, we're doing a lot of glider work. I mean, this is all high risk. I mean, we've lost 2 Otto Subs so far. One of them sitting under an ice shelf in Antarctica, and the other one we don't know where it is. I think it may be sitting on a fisherman's garden. And the other one, gliders do the same thing. Anytime you put something in the ocean and get it back, it's a bonus.
Okay.
Thank you very much.
Thanks, Doug.